Alright guys, welcome back to the last video. This one's on the other three parent functions that we'll study in Algebra 2. We're going to start off with the cube root function. We talked about the square root function in the last video. So if we have y equals the cube root of x, that would be the equation here. And we can make a little table of our x's and y's. So we can figure out what points to graph. So we want to pick x values here that we know the cube root of. For example, we know the cube root of 0 is 0. And we know the cube root of 1. And we know the cube root of 8. Right? The cube root of 8 is 2. Cube roots, you can actually plug in negative values as well, right? So the cube root of negative 1 is negative 1. And the cube root of negative 8 is negative 2. So this gives us a list of points that we can plot. We've got a point at 0, 0. We've got a point at 1, 1. We've got a point at 8, 2. And then we got a point at negative 1, and a point at negative 8, negative 2. And if we connect the dots, we see something kind of like this. A little bit of this action. Zoom. Right, so something like that. You can see from looking at the graph here, our domain is all reals. This thing goes to the left and to the right forever. And the range is also going to be all reals because it goes up and down forever as well. Reading the graph from left to right, you can see that this thing is always moving upward. So it's increasing everywhere on the domain. And it's not decreasing anywhere. It's never going down. For real. It doesn't have any maxes or mins. It does have an x-intercept at the origin and a y-intercept at the origin. Okay. And then from looking at the graph here, hopefully you can tell what the symmetry is. This thing, it's in quadrant 1 and 3, and it has the same kind of points in both quadrants, has origin symmetry. Origin symmetry. Alright, pretty quick little function there. The last two are interesting, at least. So we got exponential functions. This should be, in order to be exponential, obviously it's going to have an exponent in it. This is where you have a number as the base, and our x is actually the exponent. So like y equals 2 to the x. So we come over here and make a little table for y equals 2 to the x. So as we plug in values for x, like 1, 2 to the first, 2 to the 1 power is 2. If I plug in an exponent of 2, well, 2 squared is 4. If we plugged in 3, 2 to the third power is 8. Or if we plugged in 4, 2 to the fourth power would be 16. Right? So those are some positive values, and we're already getting to points that are not going to fit on this graph very well. Only these first three are going to fit. If we plugged in 0, well, 2 to the 0 power, we know anything to the 0 power is 1. So there's going to be a point at 0, 1. And we can also plug in negatives, right? If we did 2 to the negative 1 power, that should be a half. Hopefully you remember what negative powers do. They take the number and they flip it or move it to the other side of the fraction. If we plugged in negative 2, 2 to the negative 2 power would be 1/4. Right, so that should give us plenty of points here we can go plot. We got a point at 1, 2, at 2, 4, 3, 8. 4, 16 doesn't really fit on the graph. We got a point at 0, 1. We got a point at negative 1, 1/2, negative 2, 1/4. And as we plug in smaller and smaller powers, this is going to get closer and closer to 0. But no matter how big the number is we plug in here, and we're always going to get a positive answer. So it's never really going to cross the x-axis. It's never going to get to the x-axis either, right? So we get a curve that looks kind of like this. And it's going to follow the x-axis on the left side of the graph. Something kind of like this. All right, so that's their exponential function. And so we've talked about how it gets closer and closer to the x-axis but never quite gets there. Hopefully you remember from part 3 we talked about asymptotes. This function has an asymptote at y = 0. It has a horizontal asymptote at y = 0. So it gets closer and closer to that line y = 0, but never quite touches it. This gets really close. All right, our domain, you can see this thing goes to the left forever. It's also going to the right forever. Our domain is all reals. The y values never go below 0. They never equal 0 either. This gets real close. So our range goes from 0 to infinity, but never gets to 0, right? So we use a parenthesis. If we read the graph from left to right, you can see that it's always moving upward. So everywhere on its domain, it moves up, and it moves down nowhere. It doesn't have a max or min because it never hits a point down here, right? Even though it doesn't go below 0, it's kind of crazy to think about. There's no point on this curve that's lower than all of the others, right? It just gets really close to 0, never quite gets there. That means that it doesn't have any x-intercepts, because it never quite touches this line. But it does have a y-intercept at 0, 1. Alright, so this is just one of the exponential curves. There are lots of them, depending on what you want to make the base here. Right, so I could change this 2 to another number and make up another exponential function. So like y = 5 to the x. So if we change that number to a 5, well, what changes in the graph? Or what doesn't change in the graph, I guess. So if we plug in 5 as the base, then there's going to be a point at 1, 5 instead of 1, 2. There would be a point at 2, 25, right? Because 5 squared is 25. That's way off the graph. If we plug in 0, though, 5 to the 0 power is still 1. So it still has a point at 0, 1. That point doesn't change. And then if we plugged in negative numbers, 5 to the -1 is going to be 1/5, which is smaller than a half. So a lot of this function is going to look really similar. It only has one point in common with the other one, but the shape is the same, right? Where it wants to curve off to infinity on the right side, and then it wants to get real close to the x-axis on the left side. So this other kind of a teal color curve represents y = 5 to the x, which is a different exponential function, just with a different base. But all of this other stuff down here that we listed is the same, right? The domain of 5 to the x is still all reals. The range is still 0 to infinity. It still increases everywhere and never decreases. No maxes or mins. No x-intercepts. Y-intercept is still at 0, 1. Alright, so there are 2 examples, and again, you could change this base to be whatever you wanted. However, the most common one we'll probably see is 2 to the x. I may throw some at you from MathXL that have different bases, but that's the basic premise. Alright, and then the last function is the logarithmic function. The logarithmic function is the inverse of an exponential. So this will be our first little preview into inverses. And the equation is going to be like y equals log base 2 of x. And just like with an exponential, you could change that base to something else, right? We could do like y equals log base 5 of x. You could pick another number to be the base. So if this is an inverse, what we're doing is we're taking the points that were on 2 to the x, and we are switching the x and the y values. Okay, so this table we made for 2 to the x, we're just going to take those points and flip them. So this becomes my y value, and this is my x value. Right, so we had a point at 1, 2 on the exponential. That'd be a point at 2, 1 on the log. Let's do it this way. Let's write out our table first. So comparing it to this up here, we switch those and we're going to get a point at 2, 1. We switch these, we're going to get a point at 4, 2. We switch these, we get a point at 8, 3. We had a point at 0, 1 on the exponential. That's going to be a point at 1, 0 on a log. And we had a point at negative 1, 1/2, which is going to be 1/2 negative 1. We had a point at negative 2, 1/4. When we switch those, that becomes 1/4 negative 2. So let's go plot those points. 4, 2, 8, 3, 1, 0, 1/2 negative 1, 1/4 negative 2. Right? So we can see here that it's very much like an exponential curve. Right? It's going to curve off. It kind of looks like a square root function almost, in the sense that it has that kind of a curvy shape. But on the other side, it's going to come down and follow and get closer and closer. I did a really good job drawing this. It gets closer and closer to the y-axis here, but never quite touches it. Right, so something like this. This is the graph of an exponential function. It has a vertical asymptote at x equals 0. So it has a VA, vertical asymptote, at x equals 0, because it wants to get closer and closer to this dotted line, but it won't ever touch it. Okay, so from this graph we can see that now the domain is going to be all of the x values from 0 to infinity, and the range is everything, right? This thing goes down forever, and it also goes up forever, so our range is all real numbers. This function is increasing everywhere on its domain, everywhere from 0 to infinity, and it's never decreasing. There are no maxes and mins. There is an x-intercept at 1, 0, and there is no y-intercept. Right? So if we change that base to a 5, well then we're still going to have this point at 1, 0, because that point is on every logarithm. But now instead of having a point at 2, 1, we're going to have a point at 5, 1. And instead of having a point at 1/2 negative 1, we'll have a point at 1/5 negative 1. So it has a really similar looking curve to it, in the sense that it wants to do kind of the same thing. It looks kind of like a square root on the positive part. Then it wants to get real close to the y-axis, but never quite touch it on this part of the graph. Right? So there's our graph of y equals log base 5 of x, just to show you that you can have really similar looking shapes, but if you change that base, the points are going to shift a little bit, but it has the same shape to it, where it wants to follow the y-axis upwards and then curve off and go towards infinity. Neither one of these graphs, neither the exponential or the log graph, have any kind of symmetry to them. And yeah, I think that should be it. Right, so that's a little introduction to all of the parent functions. We will eventually come back and talk about all of these parent functions again when we get to them in our units, and we'll do transformations to move them around. So I think I might make one more day of notes on transformations just to review those things before we see them again in the individual units. All right. I will see you guys later. Have a great day. Deuces.